three scenarios. One is you can have a radio on each air vehicle. That way you can create something like a mesh networking or ad hoc networking. And we also talked about near impossibility of creating an ad hoc network in the airspace. It is nearly impossible because of the dynamics. If you think about tens of drones and you want to establish a network of drones, then because the vehicles are moving so fast, it is difficult to maintain the network. Even you somehow create a network, it's going to break. Links are going to break very quickly, right? So even though we have the idea of mesh networking, like a mobile ad hoc network, these are common on the ground, but when it comes to airspace, it's not easy. Okay, then we also considered there are other options like cellular network supported airborne networking, or of course you can use satellite also. So each of them have their own pros and cons, and specifically there is a lot of emphasis, a lot of push from the cellular service providers to come up with a framework using the cellular network or cellular service for providing communication for the drones. So 3GPP, especially new releases starting from 17, 18, 19, all these are primarily focusing on non-terrestrial networking, and that includes communication support or cellular communication supported airborne networking, right? So one thing is, irrespective of whether you use mesh networking or mesh radios or cellular service or satellite service, the discussion that we started yesterday is about drone-to-drone communications. Irrespective of the radios, irrespective of the networking support, we need to have some sort of a protocols. So that is what we are discussing. So drone-to-drone communication protocols is the center thing that we have been discussing. And today, even though on the schedule we have swarm networks, we will move that to some other day. But today I will continue discussing drone-to-drone communications. Again, my goal is to make sure that those who are working in this field or who are thinking of working in this field have something to take away from this lecture. So it is better to go in detail. At the same time, we are not discussing lots of equations and mathematical models because you can always find them on the papers. I wanted to give you a big picture first, and we'll take one problem and go deeper, just one problem. Okay. So today's talk is, so today's talk is more on continuation of what we started yesterday, and we just briefly review what we learned yesterday, and then go more get into more details. And in the afternoon, in the second lecture, I will actually look at one particular problem, a research problem, in more detail, so that if at all you are looking for a problem in this area, research problem in this area, you could pick it up. All right. So in terms of drone-to-drone communications, we looked at three perspectives, three aspects. So one is what are the use cases, and then how use cases can be implemented. So some sort of a algorithmic approach. What kind of process or algorithm will help us to implement the use case. So that's two. So use cases and implementation. Second. Third is a model where a tunable model to create a airborne network, including drone-to-drone communication, or more specifically drone-to-drone communication. If you want to establish a drone-to-drone communication link, then we'll discuss a tunable model that you can adjust according to the requirements. This particular problem is actually suggested by one of the NASA program managers, because so far in some of the research or real world applications. So for example, there was a remote ID concept we talked about. So remote ID is a broadcast message that goes from one drone to nearby drones. So typically the purpose of the remote ID is to to increase the situational awareness. For example, if every drone is sending a message, broadcasting a message, every other drone will know that okay, there is this drone present in the vicinity. So same thing happens. So if you focus on one particular vehicle, then if it receives broadcast messages from every other drone nearby, then it has an idea of the situation around it. So how many drones are present, where are they heading? So you can have something like a model within the one drone, so that it can maneuver, it can navigate, avoiding any potential conflicts. So look at this carefully. Let me repeat. A simple broadcast message from every drone in the airspace will allow every drone to have an idea about which vehicles are nearby and how far they are and which direction they are heading. So that will facilitate, that will allow the drone to navigate safely. But of course, you need to implement some algorithms and all that, but at least you have an idea. For example, let's say when you are driving, if you look around through all your mirrors, normally we do that all the time. When you look around through the mirror in front of you and the two mirrors on the sides, you have an idea about which vehicles are nearby. In fact, in the beginning when I was learning driving, I was asking one of my friends, how do you make sure that you are, when you turn, when you change the lane, there is no vehicle next to you? He said, in your mind, you always have an idea about which vehicle is next to you, because you look through the mirrors once and you have an idea about what vehicles are there, and once the vehicle passes, you know that okay, the vehicle passed, there is the next vehicle. So you always have to have that situational awareness. So that is possible with remote ID, or in the commercial aviation, you can think of ADS-B. Now, we talked about ADS-B. ADS-B is for commercial aviation, commercial vehicles, and remote ID is for the drones. So all we are doing is simply sending a broadcast message. Every vehicle sends a broadcast message. That is good enough to have a situational awareness. However, it is not sufficient for avoiding conflicts. Especially when the vehicles are so close, you need to have a two-way communication. So remember, ADS-B also provides a means to communicate. You can always send a message. You can also get a message. But what we are looking at is, when you say drone-to-drone communication, a standard communication protocol that will allow us to negotiate right of way and merging into the lane. So those are possible with V2V communications. The intention is to develop a standard, but that is probably a bit there is a long way. It's a long way. Definitely, the industry needs it, and then when the advanced air mobility services scale up, that means today we don't have air taxis, unmanned air taxis. Of course, you have air taxis with the helicopters and all that. If you want a ride, yeah, you can go for a ride, but it's not like a subway system. It's not like a regular fleet of vehicles in a city. So that will happen sometime down the lane, but even you have tens of vehicles, it makes sense to have safety mechanisms. In this case, collision avoidance is certainly a very important aspect of traffic management, and that is what we are trying to do. All these are new areas, and which means that there is a lot of potential for contribution. If you understand this, whatever you are learning today and during this week will allow you to contribute, because the subject is rich and the topic is new, and it will allow you to contribute, to make your own contributions. Okay, for example, I was talking about the idea of air cells, and it's a topic. It's an idea that started in my lab, and we presented a lot of papers, and I filed patent. My students are filing patents and all that. So same way, if you pick some topic that is connected and you think deeper, then you will be able to make some contributions. Okay? For example, the highways in the sky. This is just an idea. Nothing has been done. There are no standards. It's still evolving. So keep that in mind. It's a very rich topic that if you take up as your master's thesis or PhD thesis, there's a highly likely that you can make some innovative contributions. All right. So what are the use cases we talked about? Collision avoidance, information relay, collaborative sensing, minimum separation distance or maintaining minimum distance of separation, and airborne rerouting. These are the 5 use cases. Remember where they came from? They came from the industry. A working group called RTCA, Radio Telecommunication Association, or for avionics, I believe. So they meet quite often. In one of the meetings, in one of the recent meetings, they said, okay, what are the main applications, main use cases we want to address? And these are the use cases that came from. So what I did, I'm a chair of IEEE 1920.2, which will be released to public very soon by end of the year potentially. We are in the final phase. So in that group, we started with the use cases and investigated these use cases in more detail and came up with a set of messages and the protocol for implementing all these use cases. So once again, you remember in the discussion yesterday, I said the right way to begin to develop any standard is to start with the use cases. And obviously, you cannot enumerate all the use cases in the beginning. You may not know what use cases come up in future. Okay? So in that context, it's interesting to see things like Facebook and YouTube. We never imagined that they become so successful. They are successful because there are so many applications and use cases that came up that you never thought about. For example, I thought when Facebook came, what is the big deal having your photo? What's the big deal? But today, there are so many things. You can Facebook groups are there, especially YouTube. Today morning, I was watching when Dr. Sai Prakash visited me in the room. I was watching Schrodinger's wave equation on YouTube. Can you imagine that you learn like physics and even whatever lectures you see? This could be maybe put on the YouTube. That way, anybody can see any time. So sometimes you may not predict what use cases are going to come up. Okay. So the point is, we have 5 use cases that are coming from the users. So we dive deeply into these use cases and came up with a set of messages, okay, and protocol. So the question is it enough? No, we are releasing the standard probably by end of the year, but it may be enough or may not be enough. So one thing that I am planning to do is I will open up a competition for students and then say, come up with a use case, any use case other than this, and see whether you can use the standard that we developed and tell us whether you are able to completely implement the use case based on this, or you see any need for more messages or different kinds of messages. Okay? So I'm going to talk about what's the specific messages very soon. So the point is, that is how we evolve, that is how we develop standard. The standard is not set in stone. For example, 82.11. So today you can see a series of protocols, A, B, C, D, E, right? So things evolve. And the second important thing is, we are not focusing on which radio you are using, which frequency you are using. So in fact, to develop a standard, you also need to know what is the frequency band you are using. However, in this standard, in this IEEE 1920.2, which is for drone-to-drone communication, we have put that aside. We are not concerned about which radio you are using. So basically, it's a radio agnostic. So what does it mean? What does it mean by radio? So tomorrow, suppose the Federal Aviation or Aviation Authority in respective countries, they decide which frequency band to use, then irrespective of what frequency band, this protocol should work, because it's only a message. We are only defining messages. We are only defining the message format. We are only defining the fields within the message. We are only defining the protocol, or how you exchange information from a drone to drone. So given that, it should be applicable for whatever radio you are using. And maybe another standard might come up that will focus on which frequency band to use and all that. Okay, so it is applicable. This is not going to change. So anyway, so with respect to use cases, we spend some time. Yeah. So with respect to collision avoidance, these are the 3 things we talked about. In fact, collision avoidance collision avoidance means, two vehicles are coming closer. So if we look at what are the scenarios when two vehicles may be coming closer, these are the three scenarios. One is something called crossroads, and we in this example or in this scenario, we are looking at a situation where there is no structure in the airspace, something like in rural areas where two vehicles are flying freely, and they are sharing the messages. And what type of messages? Broadcast messages. To begin with, you are only receiving broadcast messages, and as I told you before, that is enough to have a situational awareness. Basically you know which vehicle is nearby. But if you see that these vehicles are coming closer, and if based on the information that you have about the other vehicle, if you predict there is potentially maybe a collision, then we want to figure out how to avoid. And how do you do that? Once you know the direction of each vehicle, by the way, both vehicles have the same information. Now, your information is vehicle A's information is going to vehicle B, vehicle B's information is going to vehicle A. So basically they have the same information. There is a little bit one catch, we will talk about that in a minute. So having same information, they can predict exactly which location they may be they are heading to, and the choice is now the action. In terms of action, you have to avoid that collision. To avoid the collision, what you need to do? You need to have a predefined protocol. You need to predefine, otherwise it's not possible. You don't want to negotiate in the air. You don't have so much of time. So that is one more criteria. You want to have you need to come up with a implementation mechanism or negotiation process that can be implemented in few rounds, minimum number of rounds. So that is possible only if you predefine the protocol. So as I said, the protocol could be, once they identify they are coming to the same location, potentially there is a collision, then you need to define the process. Maybe for example, one of the vehicles will go up, second vehicle may be going down, and the first vehicle again goes up and left, second vehicle may go down and right. So that way you are creating a huge gap. So again, this is something that is this one option, but we are not predefining all those. Basically, we are leaving at a point where two vehicles are coming closer and there is an action item that has to be taken by both vehicles. So this is one scenario. The second situation is a structured airspace, something like this. When I say structured, you are defining the structure, you are creating cells. We call this as an air cell, and then air cells concatenated together form a lane, and multiple lanes form a highway system. So this is something like highways on the ground, or analogous to similar to highways in the ground. You can create highways in the sky. Now, if you Google and put highways in the sky, you will see lots of articles. Potentially you will see one of my articles too. So all this is, again, at this point is all academic research. Okay? There is no real world implementation of this. And for each of these topics, by the way, there is a paper from my lab. My students have published papers, and some of them are conference papers and some of them are journal papers. So all this was actually possible because of advanced air mobility project that fortunately I was able to get in, and I was able to include my students to participate. And we are not only, in fact, before we started thinking about these problems, the real motivation is the real world implementation. So this is something different. It's not that something started in the lab and we implementing in the real world. It's the other way. We saw the real world vertical projects. We were involved in the real world projects, and we saw the potential for doing this research. So research, in this case, research is coming from the real world scenarios, real world needs. That's an interesting aspect. Okay. But then the research topics are pretty, they require a lot of investigation. For example, I mentioned about channel models. See, the thing is, there was no reason for us to even study a channel model between two aircraft at the height of, for example, 4,000 feet. There was no need, because there were no planes there is no need for creating a network in the airspace. And you might be thinking about commercial aircraft. Commercial aircraft fly at 30,000 feet. And even though the idea of ad hoc networking of aircraft has been there for long, it was in the military context. So when there is no need, who will do research and who will fund, right? So here the thing is a what you call need-based research. We saw the need, and then now we are looking at channel models. Now we'll talk about that in the next one of the lectures. All right. So merging scenario is a scenario where one vehicle from one lane is trying to merge into the other lane. And it's not only for changing the lanes, it's also for a vehicle that is taking off, just using this. So one vehicle is on the ground somewhere, or maybe on the rooftop. It is trying to take off, and then it needs to merge into one of these lanes. So merging is required while entering the highway system, or when you change the lane. The third scenario is, we call it roundabout. Basically, it's like a circular intersection. Again, we'll see this in more detail. So there also a vehicle has to enter a circle and leave a circle. So we focus on how a vehicle enters the intersection. So that's where merging happens. That's where you need to avoid collision. So collision avoidance, understanding the collision avoidance, we looked at 3 scenarios, and for each of them, as I said, we have a paper published. I will share with you later. The other use cases, I'm kind of repeating what I did yesterday, but it helps you to remember, recollect, and then understand the significance of the lecture or content here. So minimum separation is actually pretty easy, because once you know the location of the vehicle in front. By the way, before we get into minimum separation, we are imagining a scenario where a lot of vehicles are flying in the same lane. It's almost like a highway system. There is one after the other, the vehicles are flying. Okay? Like a subway system, you have 10 o'clock there is one train, 10:15 there is another train. Especially go to airport, you'll see the vehicles keep going. So there, the idea here is, as soon as you are listening, you are supposed to listen to the messages anyway. The information coming through remote ID or ADSB. So what information are you getting? You know the location of the vehicle in front of you. So the vehicle behind knows exactly where the vehicle in front of is located. And suppose the vehicle in front is slowing down. You are supposed to slow down. So that's actually natural. You don't need any protocol for that. So even though we picked 5 use cases, one of the use case, in this case, the minimum separation doesn't require any. We realize that it doesn't require any protocol implementation. But whereas the other 4, collision avoidance requires a negotiation between the vehicles. Merging requires a protocol, implementation of some sort of an algorithm or a protocol between 2 vehicles. Same thing with collaborative sensing and rerouting. Okay. All right. We discussed this before, but let me do a quick summary. Information relay refers to the information going from vehicle A to vehicle C through B. So B acts like just a relay. It doesn't do anything other than taking the information coming from A and passing it. That's information relay. And it is required because it's something like a multi-hop, routing, for example, or multi-hop information relay through multi-hop. Another example is, suppose a ground control station. I need to give a little more details about what do you mean by ground control station. Suppose a ground control station which is on the ground is trying to send a message to every vehicle in the airspace. Let's say something major, something happened. Every vehicle has to come down. These things happened, right? When 9/11 happened, we wanted every vehicle to land. And there are a couple of other situations we had that kind of incident. So what happens? From ground control, you're sending a message to one vehicle or to nearby vehicles. All nearby vehicles get the message, and each of those vehicles in turn have to pass it on to the rest of the vehicles. So, that is clearly an example, a use case for information relay. The collaborative sensing is required, is a scenario where a major event or something happened, some event occurred in the airspace, but each drone or each vehicle can only sense to some aspect of the some extent of the development, sudden development. Suppose there is a bad weather, it's raining. So, one sensor cannot look at the whole picture, and it's not possible for one vehicle to look at the extent of the sudden development or bad weather. So, then what happens? Every drone is supposed to measure, and what are we measuring? All we need to know is what is the area, what is the volume, to be specific, that you need to avoid. If it is raining in somewhere, then each vehicle will look at sense to the extent of the bad weather or raining area or volume, and then it shares that information to the ground. And at the ground control station, you can put all the information together and predict the overall extent of the bad weather. So, that in that context, that is the spirit. Potentially what could happen is, when you dig deeper, when you go deeper into a specific use case, or you look at a variation of the use case, you may find some more information that you need to, or more challenges. But for now, since we are at the beginning, there is no work done in this area. So, given that there will be first draft of this protocol, and then in future there will be more development. So, collaborative sensing basically will help to understand the scenario or the context or the hazard, we call airspace hazard, to estimate the airspace hazard fully through collaboration. Then the last item is rerouting. Now, rerouting is a scenario where, because of some weather or some other development, it's possible that there is a small depiction here, you can see. Yeah, there is probably a better figure later, but suppose you see bad weather somewhere, then we need to avoid the location. So, potentially there are two scenarios. One is the vehicle itself can come up with a new route, but if it is not aware of the full extent of the hazard, then ground control station may have to send the new route. So, if it is coming from the ground control station, then the vehicle that is directly within the range of the ground control station will get the message, but this vehicle may have to pass the information to the rest of the vehicles. So, basically rerouting is a situation where, because of some sudden changes in the airspace or sudden developments in the airspace, we have to change the route in the middle of the flight. So, to enable that, to make that happen, we need to share the information, just like similar to information relay. We may have to, for the immediate vehicles, for the nearby vehicles, you can send the new route, but if the vehicles are far away, then you have to combine this rerouting and information relay together to actually share the message. Anyway, so these are the use cases we discussed before, but now we get into some finer details. So this scenario we discussed before briefly, but again I will provide the context, and we don't go into too much into detail. The key idea here is, look at this: two vehicles are somewhere in the airspace and they are flying freely. There are no air corridors or any structure in the airspace. The process here is, each vehicle has to predict if there is a possible or potential collision, and then the goal is to avoid the collision. So, first thing is prediction. So, look at some of the circles, probably I didn't explain before. The circles refer to sensing range and communication range. Okay, there are some other important elements here are, even though you know the current location, suppose let us say this is vehicle A and this is vehicle B. Vehicle A shared the information to B and B shared with A. So, the information is already present. Now, what kind of information you have? You have the location, current location, then the direction, the speed. So, given that you can make a prediction, you know, at what point, first of all, if there is a chance of collision, and what point, and then what are you supposed to avoid? How, so this information is known, but it does not mean that you know exactly. This is only given the information at that time. Let us say you at t0 you have shared the information. So, based on the information you have at that time, you are predicting that, oh, there may be a potential collision, but you do not know exactly the intent of this vehicle. Maybe after this at t1, maybe t0 plus 1 second, it may change the route, change the direction on its own. You do not know the entire path. So, see the point, you know the intent of the, the heading of the plane, but you do not know exactly what is the next move. But typically vehicles do not change the direction randomly. So, given that, based on the information you have, you make a prediction, and then the next step is you come up with as I said before, predefined protocol to avoid the collision. So, this I think this is enough for now. Then we talked about the message, first of all, message structure. What type of messages are we going to share? So far we were able to come up with this kind of message structure. So, one message is called discovery message. So again, since we are in the beginning, we can come up with names. So, some of my students call heartbeat, and some students call it discovery message. Okay. So, but on the paper, once we finalize the draft, once we finalize the standard, there will be only one name, but you can call like heartbeat or discovery. No, these are the names we use. So, what do you mean by discovery? It's just similar to remote ID. So, in fact, I included remote ID here. And so, remote ID consists of this information. So, look at this piece. This piece of information has to be added as it is, because it's already a standard. We cannot change the existing standard. So, given that, we use remote ID as it is, and then added all these additional fields. So, this field contains, in fact, several sub fields: ID, drone ID, location and altitude, velocity, base station means ground control station, elevation, timestamp, and emergency status. This is the basic information. So, think of like every phone will send a beacon, and that is how cell tower knows you are here. So, for example, when I moved from Hyderabad to Warangal, how does the base station know that I am here? Because every second or frequently, periodically, my phone is sending a beacon message, so the cell tower knows I am here. Same way, every drone is supposed to send this as a broadcast message, like a beacon. It's as simple as that. So, but it contains the minimum information. There is a drone ID. Drone ID is something like a license plate, vehicle ID. In fact, it also contains IP address. So, in the yesterday we talked about, you are basically sharing the IP address. So, is it safe that we have to? Of course, it's not so safe, because spoofing is so much possible. So, one topic that immediately should come to your mind is, security. Security has been studied, a lot, but there is a lot more to be done. But anyway, we are not talking about security here. The drone ID is available. It also includes IP address, location, all this basic information is available. Timestamp, elevation, emergency status, all this basic. So, we are not touching that. So, when we were told that if there is a standard that is existing, you cannot override it, you cannot change it. You either use it completely as it is or don't use it. Okay? But the point is, this is not enough. We realize that this is not enough for us to establish a drone-to-drone communication protocol. So, with that, we added several fields: vehicle name, vehicle ID, priority. We talked about this a lot. We talked about priority, telemetry. Telemetry again has some information that is common to remote ID. Role. role is, suppose there are some sort of formation mechanisms, or in a military context, or even in a search and rescue operations also, it is possible that one drone may be a leader, other may be followers. So basically you can implement leader-follower model. Then in terms of priority, for now there are only 3 or 4, high, medium and low, or no priority. But typically you are basically looking at, if a vehicle is emergency vehicle, then the priority is high. So these are the fields that we developed. Yeah, we'll move on to this. For now, this is enough to enough information to see. So basically, you have an idea, no? What type of information we are including, and how does it help a given use case. So the key thing here is, whenever you are defining a standard, you need to think about, you need to have minimum information. You should not be having redundant information. You should have minimum information, but sufficient. Minimum and sufficient information. Now, of course, if you think for some reason, oh, this is not enough, you can always add. So, but to some extent, you have to think into future and define the field lengths in such a way. For example, priority is only 1, 2, 3, or 4. That means you're not putting only 2 bits over there. You're putting entire byte. So that way, in future, suppose for some reason you need to come up with 100 priorities levels, you can do that. So then normally a standardization process requires us to think ahead into future. At the same time, you don't have to define everything. Okay. Whatever information we know, whatever use cases we can think of, we fulfill them, but you can always extend. You can always extend down the line. Okay. Anyway, with that background, we learned about use cases, the 5 use cases. We learned about message structure. This is a typical structure for discovery message. And we'll talk about this called ROW, or right of way message. It is important for collision avoidance. We'll discuss that in a minute. Oh. Yes. Yeah. In fact, there also the real algorithm actually is based on typically one drone will request for right of way. So one drone will request for right of way. The drone which has high priority typically requests for right of way. Then the solution is, the other vehicle will if it accepts, it will send an acknowledgement saying response for right of way, request for right of way, and response for right of way. So request is given by high priority vehicle typically, and the response is given by the other vehicle, provided it accepts. So once you get the response, then only you can assume that other vehicle actually got your message and is honoring the message. And then the vehicle that is responding will change the altitude or will reduce the speed. So that is the simplest protocol. Okay. So once again, remember, the protocol has to be predefined. If you don't define, it will be too complicated. You don't want to run so many. You don't want to send so many messages. The number of rounds of communication or negotiation has to be minimal. So given that, we are saying just only one request and one response. That's done. So for collision avoidance, that itself that's enough. Now, unless obviously we have to test. When you come up with a standard, through simulations and through some testing, we think, oh, this is good enough, but we have to test it down the lane. And remember, as I was mentioning, these are all new area. This is a totally new area, and we haven't done a lot of testing. Even though we did something with the partner, in partnership with a company, literally we flew the drones and we tested. Okay, but it's not enough. It's not enough unless we do a lot of testing, many tests, more experiments. We cannot conclude that okay, it always works. But keeping simple is the first rule. So to do that, we should predefine the protocols, predefine some of the processes. So in this case, all we are doing is requesting for right of way and you are getting the response for right of way, and of course you still have to make sure the other vehicle actually did it, because what if something happens between after the request was honored, but then something happened. So you have to make sure that the vehicle actually is slowing down or change the altitude, then only you can continue. So those steps are still need to be followed. Okay, let's talk about merging. This we talked about this before. Merging is a scenario where a vehicle, let's assume that the vehicle that is in the pink lane or colored box is actually going towards north, and it wants to move towards west. So this is north, south, west and east. So this vehicle is originally flying towards north, and it's northbound, and is trying to move towards west. So that's, if you extend to other directions, you can, I think this is a typical diagram, and all these are called conflict points. So what it means is that if this northbound vehicle is trying to turn left and go towards direction of west, it's possible that there may be other vehicles here. So how do you handle that, right? And the solution that was designed or suggested by one of my undergrad students is very fascinating. In fact, again, what is the goal? You have to minimize the number of messages. It's not like you have infinite amount of time. You want to do it like a very effectively or efficiently using minimum number of messages. So how do you do that? Let me get to that in a minute. Yeah, here I think. Yeah. It is probably a little challenging to see this, but I will read it carefully. The first step is, this is a general merging process. Okay, so follow this. Basically, you are trying to change the lane, and potentially there may be other vehicles on this. It's a common sense solution, really, but it was fantastic solution. You will see how it is so efficient. So first thing is, listen to heartbeats. So what do you mean? What is a heartbeat? It's like a discovery message we saw before. So you know that there are vehicles nearby. So when the vehicle is trying to, for example, from ground it's taking off and it has to enter the lane, it's possible that there are vehicles in the lane. So you need to, how do you know there are vehicles? Because you have this heartbeat. You are listening to the remote ID or what I call discovery message or heartbeat message. So that means you know that where are the vehicles. Suppose there are vehicles here. Let's take the simplest case. If there are no vehicles, you don't have to worry about it. We just go. But so that is the purpose of listening to heartbeats. So it's almost like visually you are checking, are there vehicles before you merge. And instead of what you call seeing, you are actually listening to the messages, and you know if the vehicles are there, you will know and then you need to do something else. So the first question is, are there drones in the through lane? Through lane means in the main line that you are trying to merge. So that's the question we need to implement. No, then it's fine. You just merge. Nothing. You don't need to do anything. But if there are vehicles, then you are checking for, do you have enough distance, enough gap, enough space to merge? That is this question. So that means there is a conflict. If there is a conflict, then you need to, so I'll skip some of these things. If there is conflict, then you need to implement, basically you are understanding, there is a traffic. If there is traffic, you have to implement something called execute yielding process. That means you need to start an algorithm, a process. So basically you are checking the traffic. If the traffic is free, that means there are no vehicles, you don't need to do anything. But if there are vehicles, you need to begin a process. So what process is that? Yeah, we'll look at some detail. Okay. Yeah. So look at this. I think what this is demonstrating is. So what is the case one? Nothing is here. So you don't have to do anything. You're changing the lane. Okay. So this is, by the way, the one is in one direction, is this in other direction. So for example, from the previous figure, you're moving from northbound lane to westbound lane. And this is fairly easy, right? You don't need to do anything. But what about the scenario? Yeah, look at this. I'll just run it few times, then you will see the idea here. Okay. So let's understand this. Okay. So this is the vehicle that is trying to merge, and it identifies there are vehicles in the lane, so it cannot directly go into this lane, and then it has to request these vehicles, one of the vehicles, to give the gap. Okay. So imagine in the worst case scenario, there are vehicles continuously, even though we are putting one gap. Maybe the scenario that I am presenting here is that that is at least one cell gap. It's the minimum safety distance. Remember we talked about safety distance. So the point here is you are maintaining one cell as a gap, just for the minimum distance. So this vehicle is trying to get in. So let me, okay. To be able to go like this, it has to start the negotiation process. So it is going to ask one of the vehicles to give a gap. So which vehicle it should ask? There is one vehicle here, one vehicle here, one vehicle. So it has to identify which vehicle is the right one that it has to negotiate. So that's a little small, there's some process involved there. So instead of, so one idea is that this vehicle is already ahead, so you don't need to worry about this vehicle. And what about this vehicle? It remains that one of these vehicles it has to talk to. So let's check again. Yeah. So one way to think about it, it has to some sort of do some estimation saying that, okay, this is the potential vehicle that may be. It has to identify the vehicle that it potentially has a collision or a conflict. So you don't have to worry about this vehicle, but in this scenario, this has to talk to this vehicle to give enough gap. So all this is, it seems like complicated, but if you think carefully, because you know the locations, and you have to define some sort of a circle, you have to define. Let me go back for a second. It has to define, okay, which is the vehicle that it has to communicate. So in this context, it's very clearly, if it is going to merge here, this vehicle is too close. So it doesn't make sense to ask this vehicle to hold on or stop or reduce the speed. It's not going to work. So it is going to ask this vehicle to slow down. So follow this carefully. From among the vehicles that it finds potentially in conflict, it has to identify the vehicle which has sufficient gap already, and which is in a position to provide a gap or give a gap, and then negotiate with the vehicle. So that is, I believe, this idea came from just undergrad student, one of the undergrad student. So basically, to do research, you don't have to, of course, for an undergrad student, the knowledge is limited. For example, I teach communications course. For undergrad students, I teach only simple modulation techniques, like basics of AM amplitude modulation and frequency modulation, phase modulation, but they don't know the advanced techniques like MIMO and all those things. They don't know, but it doesn't mean that they cannot do research. In fact, sometimes what happens is they can do before taking the course, they can do the basic studies, learn the basics of the advanced courses, and then start working on it. And then when the time comes, when you take the advanced course, then you will be able to fill in the gaps. So to do this kind of negotiation, to do this kind of research, you don't really need to know advanced communications. For now, it is just a simple common sense logic that allowed us to allowed the student to figure out how to make this work. And another aspect is, maybe this is not coming from books, just basically thinking about the problem, spending some time, and that might lead to a solution that you are looking for. So basically, a problem was given to the student, and the student spent some time thinking about it and came up with a solution, shared with me, and typically the student has an opportunity to present with the group, because obviously we have research groups. So you present your idea to the research group, and that's how you get some feedback. And suppose you might have forgotten a certain aspect, you will know that, and that's it. That will lead you to, at least this is still research. This is a published paper, so that means there is some innovation and creativity involved in this. But later, when the student actually takes a master's level or get into PhD program, they can do even more. But the point is, you need to think through the problem, spend some time on the problem, and come up with a solution and discuss with your peers. That's what is required. So this algorithm it meets the requirements. As I said, we want to design a solution that requires minimum interaction, minimum set of messages, but yet you have to get the job done. And does it work all the time? Probably it won't. But in scenario that we described, we are assuming that all these vehicles are cooperative vehicles. So for that scenario, it works. In fact, typically, any vehicle that even flying in this corridor must have the requirement, or meet the requirements. There is an idea of requirements for advanced air mobility vehicles, which means that yes, it will be certified to fly only if it meets the minimum requirements. And what are the minimum requirements? It has to have the radio. It has to have should be able to communicate for certain range, within certain up to certain range. So all these have to be met. So the point here is, all these vehicles are expected to meet the minimum requirements. Then only they will be allowed to fly. You won't be able to fly, small drones into this area. So remember, these altitudes are about 4,000 feet. It's not set in stone, but about 4,000 feet. That means about 120 meters or so. So we're not talking about small drones. Small drones may not have the ability to have V2V communication. Okay? So with that in mind, the solution here is very elegant, very simple, and it is effective. Okay? But we have to see, it doesn't mean that's the end of the story, but over the time will tell us whether we need to have any modifications. So that's the idea. Right. So in this case, we need to think about the concept of gap. How much gap? Basically, you're asking, this vehicle is asking, create a gap for me. So that means, in this, look at the circles. The circles are giving an idea about how to choose the vehicle that you want to communicate. So for example, when you are trying to merge, this vehicle is already gone. So this is the vehicle that you need to talk. And any other vehicles, probably if there is a vehicle here, there's not enough time for it to give you the gap that you are looking for. So you have to identify the correct vehicle, right vehicle that is in a position to give you the gap that is necessary, and then this is the amount of gap that you are looking for. So this picture depicts, and finally these are the quick steps. Identifies the traffic, search for the right candidate, right drone, sends the request for gap, awaits the gap formation, and then merge. So this is what I meant by simple, sufficient, and will do the job. Yeah. So that was the merging case. That the scenario is, we talked about two, right? One is vehicles flying freely in the airspace, how to avoid collision. We talked about that. The second is merging, meaning that you are one vehicle is trying to change the lane, or a vehicle that is taking off has to merge into the highway. So we looked at those two cases. Third scenario, once again, it's a collision avoidance scenario, is something called a roundabout. This is another student, by the way, another undergrad student who designed this. Of course, he must have done a lot of literature survey to come up with the strategy, describing the geometry of the ride. So the beauty here is, you're creating a circular intersection in the airspace. Obviously, it's similar to something on the ground. Nothing, not totally new, but taking the concept of circular intersection from the ground to the airspace and working out the geometry is the innovation there. And this paper was, I told you, Not only that it was presented in IEEE Vehicular Technology Conference 2024, and when he submitted a full journal version, he got reviews, and one of the reviews were very simple. One reviewer said, "It's very pleasant to read the paper." In fact, so that's how we should be. When you write a paper, you should put all your heart into that, and make it the other person. Even as a professor, when you read the paper, you should say, there is something to learn. The innovation should come out, glaringly come out. Then people will like the paper. So and getting a paper accepted is not easy. And so many papers. One of the papers that I published. But again, most of the work is done by students. We only give the direction, idea. That paper went through 4 rounds. So it happens. It took almost 3 years to publish a paper. But once it is published, it's become a very standard, very highly cited, one of the highly cited papers. So it takes time. But the more effort you put, the more what you call time you spend to read and reread, and try to present your idea and show typically they will ask for look for what is new here. Is it what is new compared to the literature? In fact, my very first paper, when my PhD work, I did something called edge detection. When I sent the paper, they said, the review was, so what? So what means we're asking, who cares for this? So you have to justify why this is, why this is significant. What is the value? The burden is on the author, not the reviewer, not the magazine. You have to show that this is important because of this. In fact, when we write funding proposal also, it's the same thing. My program manager say, its burden is on you to show that you're doing something new, and then you are capable of doing it, and then it is not done by other people and is going to make a change. So that burden is on us. The point is, this person, even though he's an undergrad student, he was able to write a paper that other people, reviewers, felt that he felt happy to read the paper. So anyway, this is the context. So here he come up with this kind of concepts, action radius, action point, parallels radius. So read through this. The point which a US can enter and exit. So what are those? So here these are a vehicle is going towards north, enters the lane, and then it can exit from here, or it can go and exit from here, or it can go there. So basically, he identified those action points, A1, A2, A3, A4. Then he defined when do you start communication. So this term, parallels radius, is basically the radius of range of communication. First of all, that comes into the picture. So what he is saying is, when do you start communicating? In fact, I don't think I identified them here. But obviously, this radius should be it should be a function of the communication range. The radio should be able to communicate that far. And these numbers, I think these values or these variables will be clear when you look at the next. Yesterday I was looking at it, it didn't make sense in the slide, but if you go to the next slide, you'll see if you plot a graph like this, suppose r equal to 1, then you can see what exactly the meaning of r times square root 2 by 2. Square root of 2 by 2 is 1.414 by 2, which is 0.71. So these numbers come from those. Sorry. Yeah. So this, if suppose r equal to 1, then you can see this. Probably there are some minus signs that you may not be visible here. So for example, there is a minus here. You may not be able to see, but if you look at closely, you can figure it out. Okay. So basically, he designed the geometry. Ignore this for a second. Just focus on how does a roundabout look like, and then what is the need for communication. So basically, once again, you are checking for the traffic. If there is a vehicle on your way, now remember the rule in circular intersection, the vehicle which is in the circle has a high priority. So you cannot just go and enter it. Before entering, you have to make sure that you have gap. If the responsibility is on the vehicle that is entering. So, but the most important thing here is, the innovation here is how to create an artifact or a virtual roundabout in the airspace. And it is the fact that it is being reviewed, it was reviewed by peers, the peers accepted this, that itself is a sign. Your idea is not something totally out of like a wacky idea, something. So, and are they going to happen? Are you going to see roundabouts in future? May or may not. Hopefully we will see the advanced air mobility is going to be very successful. If that is, so when that happens, you are going to see all this. So, all these things that I presented, all these are, for now they are fictitious, meaning that air cell concept we talked about, lanes, corridors, all these things are, you see here and there, but that is how research starts. And one thing is we are able to go so far, and maybe we can go further because it's brand new area, very rich, okay. And then we were saying, and because vehicle to vehicle communication was started by us, in depth, not that other people don't have, vehicle to vehicle communication is for the ground vehicles exists, but somehow it didn't take off right now. So we don't, it has been more than 10 years that we had these radios for vehicle to vehicle communications on the ground, but also vehicle to infrastructure. Those standards were established, but we don't see them in action. That means we are not, somehow things didn't go the way we expected. So, but the way things go forward is some research ideas turned into standards, and then standards being accepted by the community or industry, then only things will be successful. So everything that we plan may not work out. Same thing, what I'm pointing out here, all these research ideas may become a reality at one point, but it may take longer time. Yeah, that's a good point. You brought up a good point. Why are we doing all this? To enable automation in the airspace. And why autonomy? Because that's what we want to do, autonomous vehicles, right? So you're enabling autonomy, and as I mentioned, two things are important. Vehicles have to be autonomous, and you have to manage the airspace autonomously. Okay? And then the ultimate goal is, with minimal human intervention, you want to have the unmanned air transportation with minimal intervention. I think we can take a break now, right?